longest section on work. And because you've all done MMAN2700, you know the sad part of this story is that if the truck doesn't move, the guy does no work from an engineering point of view. It's sad. All right. Cool. We'll answer this question later. I just wanted to put it up because this is the sort of thing we're talking about. All right. A cylinder of a known cross-section expands by a known distance with an internal pressure of a known pressure. The pressure's not changing, so what type of process is this? Isobaric. Good. How much work is done by the system? And so that's a cylinder with a defined geometry and defined area. The volume of an irregularly shaped balloon increases by some volume. It's an isobaric process again at a known internal pressure. How much work's done by the system? So that's the sort of thing we're talking about. So we're talking about we've got fluid contained by some fluid boundary, and the wall of the boundary is moving, and we're saying what work is done by or what work is done onto the system. Work occurs when you've got force on something in motion. Right? So work equals Fs is probably how you've seen it. We use S for entropy, so we won't use Fs, but that's what we're talking about. It comes in a couple of different forms. We'll talk about it in terms of kilojoules, total energy, specific energy, kilojoules per kilogram, and work on a rate basis. So again, kilowatts. So it has the same units as heat, which is useful because we're plussing and minusing them. When you try and minus things with different units, it's hard. Sign convention, we've talked about. It's not followed all the time. Cool. The path taken matters. So our elevation is a property, okay? So I came from my office, I walked down to get here. You guys might have come from the bus, you know, come up or whatever, or on the level to get here. We're all the same elevation, so that's a property. Work is not a property, it's dependent on the path you took. So the work that I expended to get here might be different to the work that you expended to get here. Now, let's just go through this. So work equals Fs, okay? And so a small amount of work equals a force over a small amount of distance. But if we're dealing with fluids and they're bearing on an area, you know that the force on the area is the pressure times the area, okay? Or pressure is force divided by area. So from that, force is pressure times area. So therefore we can substitute pressure area into here. But area dx, sorry where the cursor is, area dx, if you sweep an area through a small change in distance, then you sweep out a volume, okay? So area dx equals dv, and so the amount of work you do is equal to the pressure in the system times by the change in volume of the system. And if we have some way of integrating that, we can say the work done to get from state 1 to state 2 is equal to integral from 2 to 1, or 1 to 2, however you read that, of pressure dv. Okay, so if pressure's not dependent, if pressure's not a function of the path you're taking, it can come out of the integral as well. This is the maximum min in, max out. If you're getting work from a system, this is the maximum amount of work you can get from the system. So, and if you're putting work into a system, this is the minimum amount of work you need to put in to achieve this change. So you'll get slight hysteresis losses in your materials, you'll get friction. Just trying to think about some other effects that might be occurring. But if you want to achieve some compression, you need to put this amount of work in or a little bit more. And if this is work that you're getting into your surroundings, you'll get this amount of work or a little bit less. Entropy works the other way. let's have a look. Let's talk about work. So let's increase pressure and increase volume. So if we start at state 1 and we go to state 2, all right, and I've got 2 cylinders here. We're going to have a piston resting on some stops, and it's going to be constrained at the top with some stops, and we're going to do the same thing over here, have a piston resting on some stops. Now, let's do that. Cool. There's 2 thoughts. What we're going to end up with is the piston at the top with a mass sitting on it. All right? So we're going to start at the same initial state and we're going to finish at the same end state, right? But we're going to take 2 different paths. In the blue path, okay, we'll call that a blue. In the blue path, right, we'll keep the pressure low. We'll add the mass after the cylinder's lifted, okay? So the pressure is going to stay low as the volume increases, and then we're going to hit the stop, and then we're going to continue increasing the pressure until we reach state 2, and that's enough pressure to hold this mass at the top, right? But in the green state, we're going to put the weight on first, we're going to put the mass on first, and so the cylinder will stay on the bottom stops as the pressure increases. Pressure will increase to the point that there's enough pressure to lift the mass up, and then the volume will increase until it hits the stops at the top, okay? And what I wanted to point out is that if you had a snapshot of this at the initial state, right? So I should have done that's final, and nope, that's final. Okay, so if you had a snapshot of the initial states and their final states, state 1 and state 2, you would say, okay, their state properties are all the same. And in fact, the temperature needs to rise in order for this to happen. You need to add heat into the cylinders to get them to raise their pressure, right? But the work done is, and we know work equals the integral of P dV, okay? The work done is the area under this curve, because that's what integral means, right? Area under the curve. And the work done by the cylinder on the right is the area under that curve. So the cylinder on the right's done more work and in fact has had to have more heat added to it than the cylinder on the left. Okay, so that's talking about how work is a path-dependent variable and not independent like the properties of the states are. Is that okay? Yeah, go. Good. So what the difference is on the blue one, on the green one, I'm adding the weight first. Adding weight first. And on the blue one, I'm adding the weight afterwards. Or not at all. Because the piston's up against the stops anyway. So the weight isn't doing anything to move the piston. Yeah, go.
Would the same amount of energy be put into the system either way though? Just in different forms or not?
The internal energy, yeah, the internal energy is the same at the final state, but no, you need more heat put into the system to achieve the thing on the right. Yeah. And it's, so this is counterintuitive, and that's why we're learning it, I guess. So you've got delta U equals Q minus W. The cylinder on the right is doing more work. So it's having a higher negative quantity there, so it needs a higher positive quantity Q, right? So we could put like a candle or a Bunsen burner. Put a flame under here to add some heat. So work. Work good. Excellent, go.
But in that case, aren't you kind of removing yourself from the system? Because in the one on the left, you're doing the work to move the weight out. That's the difference, right?
That's right.
You're
Yes.
moving the weight, so you're not paying.
No, that's true. Yep, so on the system on the right, the system's lifting the weight. On the one on the left, you've added elevation to the weight at the beginning of the process. So yes. Yep, that's the difference. So what you need to add in heat on the right, you need to add as mechanical energy on the left. Yeah. Anyway, just raising up the two things there. One, the fact that the work is the integral of the curve under a PV chart. And two, that it's path dependent, not independent. So you can't calculate the state knowing only, you can't calculate the work knowing only the state points. You must know the path that you took to get between one state and the other. So we've got a couple of different processes. These aren't the only processes, these aren't the only ways to get from one state point to another, but these are a couple of standard ones. And we should be able to almost trivially do isobaric and isochoric. I'll show you the calculation for polytropic and then show you the solution to isentropic and isothermal in terms of work done for these processes to get from state 1 to state 2. Isochoric, what's isochoric mean again? No change in volume. If a process is isochoric, what's the boundary work? What's the work associated with a moving boundary? 0. Cool. So if you have dV, I've put the formula up in the top right hand corner. If dV is 0, okay, because it's isochoric, volume doesn't change as a function of process or time, then this integral goes to 0. So you don't get work in an isochoric space. So moving boundary work. We'll talk about some other types of work, but they're simpler. This is the work we need to calculate. Isobaric work. So isobaric work is where the pressure is constant. So pressure P is constant. If pressure P is constant, it can move in front of the integral, and you just get the integral of V between state point 1 and 2. Okay? So for isobaric work, hopefully it's work 1 to 2 equals pressure V2 minus V1. Okay? Hopefully that's fairly trivial in terms of the integration. The rest take a little bit of manipulation. So I want to show you polytropic. It's in the slides for your future perusal. And this is what it looks like. I'm going to turn around and look this way. So we start off with our governing equation, the integral of P dV, and we know that for a polytropic process, P V to the n equals C. That's our definition for polytropic processes. And so we substitute that in, we make P the subject of the equation, and we substitute that in, and we get P equaling, our integral equaling C V to the n dV, which is good, because now we're integrating volume with respect to volume. So it feels like we're going to be able to do that. The C is of course constant, so it can come out the front. This integral, right, when we integrate, we add 1 to the index and then divide by the resulting index. So we get this is the result of the index. That only works when n doesn't equal 1. So when n equals 1, you get the integral of 1 on v dv. And what's the form of the integral of 1 on v dv? Man, there's so much maths. Sorry? Logarithm? Yep. So the natural log of v. So we're going to see a natural log occur when n equals 1. So excluding the n equals 1 case, we get this between 1 and 2. So we can substitute those in. So we've got volume 2 minus volume 1. Okay? But we've got this c in here, which is just a dummy variable we've introduced. If we substitute those c's back in, c equals p1 v1 to the n equals p2 v2 to the n. And then we can get the bottom line. So we've done some substitution. All right. I've just copied the bottom line to the top line of this page. All right. But then we've got a v to the n times a v to the 1 minus n. So it feels like they can be added together. Indices can be added if you're multiplying. And we get p2 v2 minus p1 v1 divided by 1 and n. So if you know the pressure and volume of state 1, you know the pressure and volume of state 2, you know the polytropic index, n, and you know that you got there in a polytropic manner, then you can calculate the work. Yeah, go.
Is this just for ideal gases?
Is this just for ideal gases? Yes, it is. Yeah, it is for ideal gases. Pure substances don't behave in a polytropic manner. Yep. So that's a good point. For work for others, yeah, you'll have to integrate PdV. So that's our formula for polytropic work. Now, if you know pressure 1 and volume 1, so you know the state 1, you know the polytropic index n, and you know something about where it's going to end up, either the pressure or the volume, you can, of course, calculate the thing you don't know based on this equation here. So if you know the volume doubles and n equals 1.2, then you can calculate the pressure too. Sorry, my apologies. So, and you can find the work done in the process. Now, if the process is isentropic, therefore then n equals k, right? So we just replace the n with a k and we get what's on the bottom left. So that's nice and easy. If the process is isothermal, okay, so with isothermal processes, because we know PV divided by T is constant, if T itself is constant, then we find that P times V is constant, which is this, where n equals 1. So we find that we do get a natural logarithm, as you correctly said, and we find this equation in the bottom right. Yeah, go. What are the powers of n and k? The n is the polytropic index, and k is the specific heat ratio, which we'll talk about now after the break. It's a property of the fluid. So k you'll find will be a property of the fluid, and a process will follow the form PV to the k is a constant if it's an isentropic process with an ideal gas. If it's isentropic or adiabatic with an ideal gas, it'll be PV to the power of k equals C. If it's an ideal gas under compression or expansion and it's not adiabatic or isentropic, it'll be PV to the n equals C, and you'll be given a polytropic index.
If n is the polytropic index,
Yep.
it's 1 in the top line slide.
Yep.
What's the real world meaning of that?
No worries. Good. So if n is 1, what's the real world meaning of that? No worries. So I just want to explain it well. Okay. Adiabatic means no heat transfer. Okay, so say you're compressing. So we take some ambient air. I've got some air. I'll put it in a cylinder, and now I'm going to compress it. Right? I like motorbikes. Compression ratio of 18, because that's just silly. So we're going to compress it 18 times down to its volume. If I allowed no heat to escape, or I did it really quickly, okay, so heat transfer takes time. If I did it really quickly, then you would find that you'd have some pressure and some volume initially, PV to the power of in this case is going to be K because it's adiabatic. So PV to the power of 1.4 will equal something. I know what my volume is after that. It's V2. V2 is V1 divided by 18. Got a compression rate of 18. I can calculate my final pressure based on PV, now it's a much smaller number, to the power of 1.4, equals the same constant. Pressure must be much higher. Sorry, I'm doing math, which is a written language. In my head, I'm saying PV, in this case to the power of K equals C. If C is to remain constant and volume goes down by a factor of 18, right, V2 equals V1 d of 18, then pressure must go up. And in fact, P2 must be greater than P1 times 18 in that case, because of this K equals 1.4. Right? Oops, sorry. So that's your adiabatic case. If you had a real world case, what you're actually expecting, and it's also getting hotter, but it has to get hotter because PV on T is also equaling a constant, different constant. Okay? So P times V divided by T is also equaling a different constant. So therefore, if V is going down a little bit, P is going up a lot, then T has to go up as well to maintain this constant. So that's fun. So the gas is getting hotter. If you're losing some heat to the environment though, what you'll find is K won't be 1.4. It'll now become N. Ooh, can I do this? Yes, I can. It'll now become N, and it'll be a little bit less than 1.4. If you do the process so slowly and you surround the metal casing in like liquid water or something, right, at ambient temperature, what you'll find is that all the heat escapes, and you'll find that N will equal 1, so it will tend to 1, then P times V to the power of 1, P times V will equal a constant. And in fact, you'll see that come out here, where PV is a constant, the temperature must not change. So if N is equal to K, you've got an isentropic process, there's no heat transfer, that's what that means. As N tends from K towards 1, the process is becoming less efficient, you're getting more heat transfer out. As N equals 1, you've got your minimally efficient process, all of the heat is lost, the temperature doesn't change. And what we care about, so we're talking about a cylinder, so what we're just about to do is burn fuel to get it to be hot. So as much hot as it is already, oh, look at me, I should lecture thermodynamics with language like that. The hotter it is already, the less fuel you need to get it hot. So any heat you've lost to the environment during that process, and isothermal would be horrible, you've lost all your effective heat, you need to add more fuel to then get it up to temperature. So that's what N equals 1 means. So you'll find N will traverse between 1 and K. 1 means isothermal, lost all the heat generated. K would mean adiabatic, no heat. You can get N's above 1 if you had heat coming into the system. Yes, that would be that. Did that? Good, excellent, thank you. I really appreciate the question. Because I clarify things better when questions are asked. Go. You look like you were just about to ask a question. No, okay, no worries, good. You're just looking intently interesting. Okay, interested. Don't scratch your nose. I'll point to you. Radio. A couple of questions about boundary work. The polytropic index, think of it as a property of the compressor that somewhat represents the efficiency of the compressor you're using. For problems that you're given, calculation problems you're given in class, you'll be given it. You'll be told, for a polytropic expansion process, why use compressors? For a polytropic expansion process where N equals 1.3, calculate the work done by the system as it expands. Okay? For a compressor of polytropic index N equals 1.1, do this. So you'll be given it. For lab 2, you'll calculate it. You'll be given a compressor and be told, calculate N for this compressor, right? And so you'll kind of get a sense for, oh, okay, that's what N means. And it has different polytropic indexes at different operating conditions. So at different RPM and at different pressure outputs, the polytropic index changes. So it's, you know, it's one of those real world things. K is really nice because it's something that's universal. You can read it from a table, you can use it all the time. But N is what we see happen in the real world. So that was my little bit more. Let's not get bogged down on it. We'll understand a lot more of it after Lab 2, which I think you guys do in week 6 and week 7. Excellent. Let's do some math. So this is work. This is boundary work, related calculations. A cylinder of cross-section area. Area expands by distance d with an internal pressure of P. How much work is done by the system on the surroundings? And I want to take this at two different approaches on this, because I want you to see that you could do this more traditionally using potential energy, but I want to do it using pressure so you can see they're equivalent. I hope they should be. All right, so we have said that work from 1 to 2 equals, it's isobaric, the pressure doesn't change, which is nice, so it's pressure, volume 2 minus volume 1. We don't know what the initial volume was, but we know that some area is swept through some volume, so we know what the change of volume is, so that's nice. All right, so delta V, and I should do that so we're not confusing with velocity. Delta V equals area times delta X for us, right? 0.15 times 0.2, 0.03. If I get my math wrong, it's totally because I'm testing you and not because I occasionally get my math wrong. So that's our delta V, all right? Our P is given, 500 kPa, and our delta V is given 500.3. 15. I also have a cheat sheet. 15 watts. No, because watt's also a unit, so that's not true. 15 watt is the unit. Kilojoules, happy with that? Good, cool. So we've carried our kilo through, and a Pascal times a meter cubed becomes a joule, because a Pascal is a Newton per square meter, and so it becomes a Newton meter, which becomes a joule, which is excellent. All right. How much weight would we need? Okay, so that's solution 1, okay? But you already had a solution, you already had a method of solving this, right? How much weight do we need to maintain a pressure of 500 kPa over an area of 0.15 meters squared, all right? So this is force equals, force equals pressure times area, all right? So we've got 500 kPa times 0.15. Feels like it should be 75. Is that about right? Good. So we're talking about a cylinder, what's 0.15 meters squared? Talking about a cylinder like yay, we've put 7.5 kilos on it, and we've compressed it up to 5 times atmospheric. What we'll actually find is that the amount of weight, if we put a mass, like a lump of mass on there, we'd find we need less than that because the atmosphere itself is also giving us some pressure. We'll talk about that soon. All right, and what was our distance? We said our distance was 0.2 meters. So if we said work equals force times distance, okay, then we'd say 75 newtons times 0.2 meters, and we'd find that that should have been a kilonewtons. That looks better. So put 7.5 tonne, that feels better. That does feel better. Good, good. So put 7.5 tonne on top of the cylinder. So compress it to 5 atmospheres. Okay, and so we've lifted that then force. We've had motion against an opposing force. And we find that we have the same amount of work done. Right, so this is just showing that you can use pressure and volume, which is what we've just learnt. Or we could have used, that sounded expensive, we could have used force times distance, which you already know. Okay, so you had a way of solving this problem. Cool. Questions from that? Excellent. What using pressure times volume lets us do is solve this question then at the top left-hand side. Sorry, I can read that because I'm quite close to it. At the top. So what if we had some arbitrary irregular shape? Okay. The volume of an irregularly shaped balloon increases by volume. It's an isobaric process at some internal pressure. How much work's done by the system? Well, in this case, you don't need to know what the shape is, and it's not necessarily lifting a weight in that sense. You can't necessarily think of it in that sense, but you can do work from state 1 to state 2 equals pressure times the difference in volume. We're given a pressure, we're given the volume. They're the same numbers as before because I'm lazy. No, but I just wanted to explain that the concept is the same and not go through a different set of math. Cool. And the last one, which is different. So a cylinder with a cross section given, so we're using the same cylinder. Now we need the initial volume. So I've had to define the cylinder a little bit more. So 1 meter tall, it's compressed by some distance. So it's compressed from 1 meter to 0.8 meters in an isentropic manner. So K equals 1.4. So this is our, so we're talking about a polytropic process where K equals 1.4. The initial internal pressure is 500 kilopascals. How much work is done by the system? See it? Good. Okay, so now we're saying PV to the K is some constant. We've got a pressure 1, we need our volume 1. Volume 1 equals height times cross-sectional area. 1.5 meters squared. Cool, so we've got our initial volume. We can get our volume 2 while we're at it, 0.8 times 0.15. Yeah, so we've got a cylinder and we're compressing it. Yeah, 0.8. 1. Cool. Volume 2. Any takers on that? Have I got it written down? 0.12. That sounds like 80% of 0.15. Yep. Agreed. Volume 2. P1 equals 500 kPa. All right. That looks like the things we need. Work from 1 to 2 equals, let's check their PowerPoint slides. It's isentropic. So we're going to use the equation from the bottom left-hand corner. P2 V2, P1 V1, 1 minus K. P2 V2. Okay, looks like we need P2. All right. So to get P2, we're going to use this equation on the top right-hand side. So P1 V1, oops. KPA. What's P2 equal when you get there? I'll clean up my letters. That's not what I got. Hang on. 1 divided. Is it? No, good. Excellent, good.
Do we need to know the derivations for...
Do you need to know the derivations for the formulas?
Yeah.
I don't know. I don't think so. I don't think so. It used to be a big part of the subject. I want to move this subject away from calculations and mathematics, although it's definitely founded on that, and I want to move it towards understanding and application. So I've got to drop something, and so what I'm going to do is provide formula sheets. I'll provide the formula sheets a few weeks before the class test. I haven't written it yet, but I will write it and I'll give it to you, and you'll know these are the formulas I don't have to remember. And if there's something important you saw that you don't see in the formula sheet, you maybe need to remember that. I'll try not to be like that though. I think you should be aware that all this stuff just comes out of maths you already know, but I don't think you should be able to reproduce that under exam conditions. Yep. Good question. Did anyone do that calculation? Good. 83.4, I'll pay that. Kilopascals. So now we've got, what do we got? We've got P2, V2, P1, V1, we've got K, excellent. So, work. I'm using subscript 1, 2 here, so this is work from state 1 to state 2. When we've got processes when we've got cycles that have many state changes, it becomes important to say, what are you talking about? We're talking about the work that's done between state 1 and state 2. Equals, so what are you? 683.4 times. Minus 500 times. Okay, excellent. This is a do yourself at home, but I got 17.5 kilojoules of work done. And tap, by all means, tap the calculator, check yourself. It's a negative. It's not a smudge. It's a negative out the front, right? So that says that when we compress something, when we compress a cylinder, it's the surroundings doing work on our system, so it's negative work, okay? So, and that comes out of using the formula correctly. You just want to validate that and check and see what's going on. The other thing we can calculate is we can calculate T2, which we won't do, but we can calculate T2 and show that in fact the temperature must have risen. Okay, so that would come from our combined gas law that says P1 V1 on T1 equals P2 V2 on T2. I didn't give you a T1, but you just say ambient conditions, 20 degrees C. Right? This ratio only works if these temperatures are in Kelvin, okay? But you can satisfy for yourself that when you compress an ideal gas ideally, the temperature rises. And that's not necessarily something that's intuitive. I had someone ask me a question UNSW Uni Day, and they said, what do you teach? I said, thermodynamics. They said, oh, how does an air conditioner work? And I said, well, you know when you compress a gas and it heats up? Like, no. And I'm like, that's because you're in year 12 and you haven't learned thermodynamics yet. What about, yes, you're right. I should have said, you know, like when you're pumping up your tyre on your bike and the tyre gets hot? I love it. Kids these days don't write about it. Yes, all right, good. Moving boundary work. So we've done that. So if your fluid is moving against some external force in the surroundings, or the surroundings are working on your fluid, you've got moving boundary work. There's a couple of other types of work that I wanted to talk about as well, because we've got a turbine, denoted here in the bottom left-hand corner as turbine. That's how you can tell it's a turbine. It's got some power coming out of it. This is a steam turbine, probably. Let's call it a steam turbine. This is part of a Rankine cycle. This is what's generating most of the electricity that we use in the room. And the casing on the turbine doesn't move. Turbines don't grow and shrink, well, they thermally grow and shrink, but not by very much. And when they're at standard operating conditions, or steady operating conditions, they certainly don't. So what's expanding? What force is moving against? What are we forcing against an opposing force? And this is what the inside of a turbine diagrammatically looks like on the bottom right-hand corner. Typically on the outside, you've got what's called a stator. So just like in an electric motor, things that stay still. And you've got, in this case, nozzles. So the flow is going from the left-hand side to the right-hand side on this diagram, okay? And so they are forcing the steam that's coming in to go up the page, okay? So they're forcing the steam around. And so a turbine actually is trying to rip itself out of the floor with torque. You've got to bolt them down really securely, right? Because all the steam is forcing the turbine to twist one way. And then the rotor, which is these, you've got blades on the rotor, and they're connected to the inside. So the rotor, the hub, is turning, okay? And they are using little cups to catch that and try and force it back down the page. So, and the change in that momentum, you're going to do this in 2600 as well with the Pelton wheel, same sort of thing. So the change in that momentum is forcing the inner hub to rotate. And as it's doing this, the gas is expanding. So as it undertakes this work, it is expanding. So it's moving boundary work, but it's internally, well, it's not moving boundary, but it's internally moving work. We'll say that shaft work, we'll call it shaft work, and shaft work equals, so the overall work is 2 pi times the number of revolutions that you undertake, times by the torque that you get out of that. And you probably do something similar in 1300. You talk about shaft work. You can differentiate that with respect to time and talk about power being 2 pi n dot, or if you put n in radians per second, it's just the radians per second times by the torque. That's the power you get out of a turbine. So this is what's happening inside. It is moving boundary, but it's just encapsulated. So we care about shaft work because one of the main outcomes of thermodynamics is shaft work. We want work out of a turbine. You could consider a crank to be a shaft, but we won't. We'll talk about the cylinder. This is a picture of a turbine. These things can be big. You can buy them. You can look them up. You can study them for your assignment if you would like to. This is obviously the rotor, so you can see the blades on the inside. Have you guys done the torque it takes to tear a steel shaft yet? Or is that 2400? Good. Not so yet. Rightio. When you're doing that, right, say this guy's like 2 meters tall, so say he's about a meter from his belt to his hand. Oh, that's earlier in shot. When you get to that calculation, throw yourself in a 350 megapascal yield steel shaft that's a metre in diameter and see what kind of torque you're talking about to tear this thing apart. Other work that we might talk about, we talk about electrical work. If you're willing to accept it, you are forcing electrons past their ability to, their tendency to stay still, right? The integral of voltage times current over time, right? So power equals VI, so the total work would be the integral of that over time. We talk about spring work. So if you're compressing a spring, you're doing work on that spring to compress it. Elastic deformation is the same sort of thing. This is just like a solid steel bar or elastic energy. Yeah, again, we don't want to go too much into these sorts of things because this is really solid mechanics. The beauty of engineering later on is you get to combine these sorts of things together and build complex systems. I want very simple mechanical systems so you can focus on the thermal part of the cycle. But we need to be aware that that exists. And of course, potential energy or kinetic energy. So these are places that our work could go that may or may not involve moving boundaries for us. That was work. Does anyone want to talk? So heat was like 3 slides. It's transferred across the boundary. We're going to talk about it later. Work was like, hey, let's actually get into what's going on.